Drop a ball. It falls straight down, predictably. And for 300 years we told ourselves a story about why. Something invisible reaches up from the earth and pulls. A force. Gravity. Newton gave it a formula. Textbooks drew arrows pointing down. We learned to calculate trajectories, launch satellites, predict tides, all with this idea of a force tugging at everything. But here is the problem. The ball doesn't feel anything pulling on it. A person in free fall feels weightless. No force, no pull, nothing. An astronaut orbiting Earth isn't fighting gravity, they are falling, endlessly, and yet they feel absolutely nothing. Einstein looked at this in 1907 and asked, what if the ball isn't being pulled at all? What if there is no force? What if what we call gravity is just geometry, the shape of the universe itself, telling objects where to go? This is not a metaphor. This is literally how the universe works, and once you see it, you cannot unsee it. In 1687, Isaac Newton published the Principia. In it, he described a force that acts instantly across any distance. The sun pulls on Earth. Earth pulls on the moon. Every object with mass attracts every other object with mass. The formula was elegant. Force equals G times M1 times M2 divided by R squared. It worked beautifully. It predicted the orbits of planets. It explained tides. It launched the age of precision astronomy. But Newton himself knew something was wrong. The force in his equation acts instantaneously. If the sun disappeared right now in Newton's universe, Earth would immediately fly off in a straight line, no delay, no signal travel time. The gravitational rope snaps across 150 million kilometers in 0 seconds. Newton called this action at a distance and openly admitted he had no explanation for it. In a letter to Richard Bentley, he wrote that the idea of gravity acting through a vacuum without any medium was to him, quote, so great an absurdity that no man who has any competent faculty of thinking can ever fall into it. He knew his theory described what gravity does, but it couldn't explain how. For over 2 centuries, nobody could do better, until a patent clerk in Bern started thinking about elevators. In 1907, Albert Einstein was sitting at his desk in the patent office when a thought struck him, one he later called the happiest thought of my life. He imagined a man falling from a roof. During the fall, the man would feel weightless. He wouldn't feel any force of gravity at all. His keys, his wallet, everything around him would float alongside him, exactly as if he were in deep space, far from any planet. Einstein realized something profound. If you cannot tell the difference between floating in space and free-falling toward Earth, then maybe there is no difference. Now flip it. Imagine you're inside a closed elevator. No windows. You feel your feet pressing against the floor. You feel weight. Is it because you're standing on Earth, or because the elevator is accelerating upward through empty space, pushing the floor into your feet? No experiment you perform inside that box can distinguish between the two. Drop a ball, it falls to the floor either way. Pour water, it flows downward either way. Measure your weight, same number. This is the equivalence principle. Gravity and acceleration are indistinguishable. Locally, they are the same phenomenon. And if they are the same, if the pull of gravity is identical to the floor accelerating into you, then maybe there never was a pull. Maybe what we call gravity is not a force acting on you. Maybe it is the ground accelerating upward to meet you. But how can the ground accelerate? It's not a rocket. The answer requires us to abandon flat space. You have probably seen the analogy. A bowling ball on a rubber sheet making a dip and a marble rolling toward it. This is how most people picture curved space. It's wrong. Fundamentally wrong. First, it uses gravity to explain gravity. Why does the marble roll toward the dip? Because of gravity pulling it down in the real world. It's circular reasoning. Second, it shows curved space. But Einstein's insight is about curved space-time, and the time part is actually the dominant effect for everyday gravity. Here on Earth's surface, space is barely curved at all. If you measure the circumference and diameter of a circle on the ground, they match Euclid's formula to extraordinary precision. The curvature of space near Earth is negligible. What is curved, dramatically, is time. Time passes slower near massive objects. A clock on the floor ticks slightly slower than a clock on the ceiling. This difference in time flow is what causes objects to fall. Forget the rubber sheet. What you need to picture is not a dimple in space. It is a gradient in time, where downward is the direction where time flows slowest. To understand how time curvature makes things fall, we need one concept, the world line. Everything in the universe traces a path through space-time, not just through space and time together. You, sitting still right now, are moving through time at 1 second per second. That's your world line, a straight vertical line going upward through time. Now here's the key. In flat space-time, where there's no mass nearby, the straightest possible path between two events is a straight line. Objects in motion stay in motion, Newton's first law. But mass curves space-time, and in curved space-time, the straightest possible path, called a geodesic, is no longer what you draw with a ruler. Geodesics curve toward regions where time passes slower. Think of it this way, an object always wants to travel the path where it ages the most, the path of maximum proper time. Near a massive body, time runs slower, closer to the surface, so the path of maximum aging curves away from the surface. But you're standing on the surface. The ground blocks the geodesic. The ground pushes up on your feet. You are the one being accelerated. The ball, when you release it, simply follows its geodesic, the straightest path through curved space-time, and that path converges toward Earth. The ball isn't pulled, the ball is free. You are the one being pushed. This is general relativity. Mass tells space-time how to curve. Curved space-time tells objects how to move. No force required, no invisible rope, just geometry. Einstein spent 8 years, from 1907 to 1915, developing the mathematics for this. The result? His field equations. 10 interlocking equations that describe precisely how mass and energy warp the fabric of space-time. A beautiful theory means nothing without evidence. Einstein's geometric gravity made 3 predictions that Newton's force-based gravity could not match. Mercury's orbit. For decades, astronomers had noticed that Mercury's closest point to the Sun shifts slightly with each orbit, a precession of 43 arcseconds per century that Newton's equations could not explain. Leverrier first noticed this anomaly in 1859. People proposed a hidden planet, Vulcan, to explain it. Einstein's curved spacetime produced exactly 43 arcseconds. With no hidden planet, no free parameters. When Einstein completed this calculation in November 1915, he said his heart palpitated. Light bending. If spacetime is curved near the Sun, then light, which also follows geodesics, should bend as it passes nearby. Einstein predicted a deflection of 1.75 arcseconds. In 1919, Arthur Eddington photographed stars near the Sun during a total solar eclipse and measured 1.75 arcseconds. The next morning, newspapers around the world declared Newton dethroned. Time dilation, clocks closer to a massive body tick slower. Today, every GPS satellite proves this. Satellite clocks orbit at 20,200 kilometers altitude, where gravity is weaker. Their clocks gain 45 microseconds per day from reduced gravitational time dilation, lose 7 microseconds from their orbital speed, for a net gain of 38 microseconds daily. Without relativistic correction, your GPS position would drift 10 kilometers per day. Every time you navigate with your phone, you are relying on Einstein's geometry being correct. Einstein's equations had one more prediction, the most dramatic. If space-time is a fabric that curves, it should also ripple. Disturbances in space-time should propagate outward at the speed of light, like waves on a pond. Gravitational waves. Einstein predicted them in 1916. For a century, nobody could detect them. The effect is absurdly small. Then, on September 14, 2015, two detectors, one in Louisiana, one in Washington state, simultaneously registered a signal. Two black holes, each about 30 times the mass of the Sun, had been spiraling toward each other for millions of years. In the final fraction of a second, they merged. The collision released more energy than all the stars in the observable universe combined, and it came out as ripples in space-time itself. The distortion that reached Earth, 1/10,000th the diameter of a proton. Space-time stretched and compressed by less than the width of an atom's nucleus, and we measured it. Gravity is not a force. There is no invisible rope, no pull, no tug. There is only geometry. Mass warps the fabric of space-time. Time flows slower near heavy objects, and everything, planets, photons, you, simply follows the straightest path available through that curved landscape. Newton gave us a useful formula. Einstein showed us what's actually happening. The universe is not a stage where forces perform. The universe is the performance. Its shape, its curvature, its geometry, that is gravity. The next time you drop something, remember, nothing pulled it down. The ground rushed up to meet it, and the object was free the entire time.